Welcome to today's webinar with Vitech Principal Systems Engineer Gareth Digby, who is presenting on connecting GENESYS to the analytical engineering environment. My name is Katie, Communications Manager here at Vitech, and I will be your host during today's presentation. Gareth is a member of our professional services team here at Vitech and mentors clients on the use of model-based systems engineering to deliver successful systems designs. In addition, he trains clients on systems thinking to analyze and assess systems-based problems. He focuses on capturing and understanding customer requirements, developing system architectures, and transitioning solutions relating to the application of computing, networking, and communication technologies across multiple industrial and commercial sectors. Before Gareth gets started, I do have just a few housekeeping items. We will be answering questions today at the end of the webinar. Please send your questions in as soon as you think of them through the Question tab on your webinar control panel. Gareth will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded today. If you experience connection problems during the live presentation, a recording will be available on our website within about 24 business hours of the live version. I will send out the link into the chat window of where that will be located. I will now turn the presentation over to Gareth. Welcome and thank you for joining us.
Good morning. Thank you for attending my webinar on connecting GENESYS to analytical engineering tools. I just want to check with Katie. Has the screen changed okay, Katie?
It has.
Thank you. This morning, I will discuss how we can use systems engineering tools such as GENESYS to move beyond simply supporting model-based systems engineering to providing an integrated model-based engineering solution. I will introduce some of the issues we have in systems engineering. We will look at model-based systems engineering and consider some of the approaches that provides to break the barrier between model-based systems engineering and an integrated model-based engineering solution. Using engineering analysis as a focus, we will review how the implementation technologies we use for breaking the barrier can impact our ability to achieve an integrated model-based engineering solution. I will then discuss how GENESYS 4 is implemented using technologies that can help address these issues and allow us to cross the barrier to deliver an integrated model-based engineering solution. This is the problem that model-based systems engineering set out to solve. While hopefully our desktops are not like this physically, the problems we face can appear this way figuratively if the tools supporting us are not appropriate. But in all seriousness, the key takeaway here is that a change in any one area has impacts in many other areas. In ambient findability, Peter Morville states that people will not seek information that makes their job harder, even if it may benefit the organization they work for. Clearly, on this desktop, information is hard to find. But as we move towards making information more accessible and potentially easier to find, we have to consider three aspects associated with the ease of access. Firstly, the mechanics of retrieving the data. Secondly, the structure of the data so that when retrieved easily, associated data is also found. And thirdly, the meaning of data should be obvious so that it is easily understood as information. The International Council on Systems Engineering Vision 2025, has a number of challenges that have been identified that must be dealt with as the profession continues on the path to provide future integrated interdisciplinary solutions. For this presentation, I would like to draw out two of those challenges. Firstly, knowledge and investment are lost at project lifecycle boundaries. increasing the development cost and risk of late discovery of design problems. And secondly, technical and programmatic sides of projects are poorly coupled, hampering effective project risk-based decision making. The systems we are delivering today are not the complex electromechanical behemoths of the past, but extremely complex, geographically distributed, software-intensive, cyber-physical systems. The rate of change of potential application areas for model-based systems engineering is growing faster than the rate our systems engineering tools can include specific features for those particular application areas. Therefore, rather than build tools that can cope with every eventuality, we need to build tools that have the flexibility to adapt to any application area, so that the users can bring the features they need with them to the systems engineering tools. Let us look at model-based systems engineering and how it intends to get us away from the document-filled desktop and help make data more accessible. Model-based systems engineering is moving systems engineering from a document-centric to a model-centric practice. However, in ambient findability, Peter Morville states that the document will endure as long as we do, for it is not tied to technology, but like space, time, and hierarchy, is a construct of the human mind. So what does that mean in practice? Model-based systems engineering seeks to increase the visibility of systems engineering information while at the same time reducing errors through the use of a centralized model that is accessible to all of those involved in the engineering process. While we may not have removed documents entirely from our process, the intent is for the documents to be generated from a single source. We have one model that coordinates them all. Model-based systems engineering is allowing systems engineers to move away from documents and use models comprising rich structural notations that can be viewed both graphically and textually. The systems engineers are able to do design instead of simply managing documents. The systems engineers provide the intellectual property, and the systems engineering tool manages the resultant documentation. The systems engineers and discipline engineers are able to use the centralized model as they undertake their engineering tasks. Data and expertise are brought together by a systems engineering process that uses the model to create the system design, and the model becomes the source of the specifications and the reports on that design. The model-based systems engineering applications allow the systems engineers to perform a large number of tasks associated with designing a solution. These include analysis, synthesis, verification, and validation. The models allow the systems engineer to capture the data associated with the system design. The data is held in terms of a system definition language and an associated graphical constructs. This provides structure and meaning to the data so that it can be presented as information in a consistent manner and discussed and argued about in a formal way. Our system engineering models reflect the systems engineering information that we have entered into them. However, the models are providing views onto the information through the lens of the systems engineering profession. While this is very valuable for both the systems engineers and the discipline engineers, it does not allow the discipline engineers to do all their tasks using the model. Although sophisticated, the model-based systems engineering applications are not able to support all of the detailed numerical analysis that the discipline engineers and some systems engineers need to undertake as part of their design activities. We need a mechanism to allow the models and their data, rather than the model-based systems engineering applications, to support all the detailed numerical analysis that the systems engineers and the discipline engineers need to undertake as part of their design activities. Let us look at some of the needs of engineering analysis. It is vitally important that the data used by the discipline engineers as they make their decisions about the system solution come from a common source. Therefore, it makes sense that the data should come from the centralized model. The discipline engineers need the data in a structured form that's applicable for their analysis. They also need data that is meaningful for the analysis they are performing. The goal is to move from just model-based systems engineering to digital engineering. Ideally, we would like to achieve a situation where both the systems engineers and the discipline engineers can perform analysis and undertake design concurrently using a common pool of data and information. So, as the systems engineers alter their aspects of the system's design, the discipline engineer's analysis immediately reflects the changes instigated by the systems engineers and vice versa. GENESYS provides some analysis capabilities through its simulator, which allows the behavior of the system to be analyzed using an event-driven simulation. The simulation is sophisticated and can take into account a number of aspects of the design and its potential implementation, including the synchronization of behavior through the issuing and receipt of messages, the production, consumption, and capture of resources by the system, the impact of message size and interface bandwidth on message latency and transmission rates. But we are not able to do analysis such as continuous signal analysis within GENESYS, or at least we are not able to do it without writing our own custom scripting code. For example, we could not do any electrical voltage analysis as we look at size, weight and power and cost, or swap-C data in our model. So, while the systems engineering model holds data that will be used by the discipline engineers, the models do not provide the necessary means of using that data in a manner that is relevant for the discipline engineers. Let's broaden our discussion to look at model-based systems engineering data exchange. Traditionally, detailed numerical analysis has required the movement of data between applications, typically as part of a manual process. Often this manual movement would be in the form of an electronic document. The structure of the document would be familiar to the recipient, and they would be able to navigate through the document to gather the information they need for the analysis they are going to perform. The document is in a form that's appropriate for their discipline. Nowadays, the manual process for exchanging data manifests itself as the export of a file from one application, which is then imported into another application. The information that results from the engineering analysis of the data is then passed back to the centralized model in a similar manner through the use of files. The creation and distribution of files can lead to the introduction of errors. Files can be corrupted or altered, either accidentally or maliciously. In addition, the information is likely to be resident in multiple locations, and therefore it is hard to keep the information synchronized as time moves on. This lack of synchronization results in islands of data. The data being exchanged in the file will be written in accordance with a set of rules, a syntax, so that the exchange of data is repeatable. For the data to be information for the recipient must understand the meaning of the data described using the syntax. Meaning is provided through semantics. Let us consider fully connected model-based systems engineering and how it helps with data exchange and provides a path for integrating with our engineering analysis tools. Our goal is the connection of systems engineering models to analytical engineering tools and other discipline-centric applications, so the data can be used directly without the need to transfer via files. Before we look at how the technology used by GENESYS moves us towards our integrated model-based engineering environment, let us consider the scenarios GENESYS can support when it provides an integrated model-based systems engineering environment. GENESYS is built in layers. A database to hold the model repository is accessed and interacted with via a collection of services. The GENESYS user application accesses the GENESYS services via an application programmer interface. The user views the model using the GENESYS user application. In the simplest case, GENESYS can be used in a standalone mode. Providing access to the model repository database via services provides a number of benefits. Another GENESYS user application on a different computer but on the same local network or workgroup is able to call those services and access the models on the other user's computer. As expected, this workgroup access to the models is controlled via appropriate permissions, etc. For a large team spread across an enterprise network, the models can be held on a central enterprise GENESYS server. The GENESYS user applications access the enterprise GENESYS server using the same application programmer interface. The flexibility provided by the use of services and the definition of an application programmer interface opens up numerous possibilities. Secure access can be provided to the model repository for other applications. Connector plugins to other applications can be developed which leverage the application programmer interface. At Vitec, we have already developed and provide connector plugins for Microsoft PowerPoint, Microsoft Project, and Microsoft Excel. The Microsoft PowerPoint connector allows the Microsoft PowerPoint application user to access the various graphical views available in GENESYS and import those graphical views onto slides within Microsoft PowerPoint for presentation using Microsoft PowerPoint. The Microsoft Project connector allows the Microsoft Project application user to access the model and retrieve the project management related information. Microsoft Project is then able to present this information using its views. The connector plugin that has been developed for Microsoft Excel allows the Microsoft Excel application user to directly access the model. Microsoft Excel can then be used to retrieve data from the model and send data back to the model. Not only can existing model data be modified, but new model data can be created in Microsoft Excel and placed into the model. In addition to the 3 connectors for the Microsoft products, GENESYS is also able to access IBM Doors as a client and exchange data with a Doors repository. These connector plugins clearly lead to improvements in visibility and communication between the systems engineering team and those outside the systems engineering team. The connectors allow the users to access data directly and immediately. The issues associated with data aging are removed. Errors due to corruption of data files are also removed. We have achieved our goal of connecting the systems engineering model to other applications so the data can be used directly without the need to transfer via files. But have we achieved the goal of connecting to analytical engineering applications? How do we go further and allow the discipline engineers to bring their own analysis tools to the data residing in the systems engineering model? This connectivity is achieved by GENESYS using a publicly available application programmer interface. The application programmer interface allows any application access to the data within the model. The application programmer interface provides a set of rules, a syntax, so that the data exchange is repeatable. The removal of file-based exchange prevents islands of data being established. The application programmer interface significantly reduces the likelihood of errors as the manual steps in the file exchange have been removed. For data to be information for the recipient must understand the meaning of the data described using the syntax. Meaning is provided through semantics. The semantics for a particular discipline or subject matter expert are encoded in the application that's using the application programmer interface to retrieve the information. Let's look at the mechanics for using the application programmer interface. Our GENESYS product is structured like this. The GENESYS model consumer uses the client application programmer interface to access the data. The client application programmer interface uses the Microsoft.NET conventions. The client application programmer interface accesses the services layer using the standard Windows communication foundation stack so that it can be deployed flexibly on typical hardware, software, and network configuration. The services connect to the database in order to access the data. The database is on the local host or within the local workgroup as a Microsoft SQLite database, or on the enterprise network as a full Microsoft SQL database. It is the GENESYS model consumer that applies the semantic meaning to the data to turn it into systems engineering information. The disciplines are able to develop their own model consumers that provide them with the data using their semantic meanings. These model consumers could range from dashboards within Excel to complete applications. Should you decide you want to develop your own model consumer to leverage the data in a form that's directly meaningful to your discipline, Vitec provides documentation with GENESYS to provide help on the application programmer interface, including a Getting Started guide and a set of application programmer interface documentation within the GENESYS help information. In addition to the help documents, 2 Visual Studio sample projects are provided, demonstrating the use of the application programmer interface. Alternative approaches are available for the use of Alternative approaches are available to the use of Microsoft .NET libraries for creating application programmer interfaces. For example, Open Services for Lifecycle Collaboration, OSLC, defines representational state transfer, or REST or RESTful, application programmer interfaces that use HTTP-based operations to create, read, update, or delete data. Open Services for Lifecycle Collaboration uses Resource Description Framework, or RDF, to define the capabilities of the RESTful application programmer interface. GENESYS is able to act as a consumer using the Open Services for Lifecycle Collaboration defined RESTful application programmer interface in order to access data held in an IBM Doors repository. The IBM Doors repository acts as a provider to the GENESYS consumer. So, in conclusion, we have seen that the design of GENESYS to use services and to provide a public application programmer interface allows us to achieve our goal of providing fully connected model-based systems engineering. In 1959, Calvin Moores stated that an information retrieval system will tend not to be used whenever it is more painful and troublesome for a customer to have information than for them not to have it. The mechanisms discussed today provide transparent access to data and information. Through the use of these techniques, we have reduced, if not removed, the friction associated with accessing data. Those within or outside our systems engineering team will have to find other excuses for not using our information. We are able to connect analytical engineering tools to our systems engineering model. The analytical engineering tools provide the semantics to the data so that it is meaningful to the discipline engineer. The systems engineers and discipline engineers can perform analysis and undertake design concurrently using a common pool of data and information. The model is the repository for our data. We have moved towards making information more accessible and potentially easier to find. We have shown automated mechanisms for retrieving the data. The data is structured according to a syntax so that when retrieved, the associated data is also retrieved. The meaning of the data is defined in the application that the user uses so that the data is easily understood as information. So, thank you, and now back to Katie.
All right, thank you so much, Gareth. We do have a few questions. The first one is from Jeff, and he asks, could you give an example to show what you mean when you talk about syntax and semantics, and how the semantics will be provided by the analytical engineering tools?
Okay. Let's think. An example of syntax from the VITEC system definition language would be that of a requirement specifies a component. So specifies is the word we use to in the syntax for that relationship. So for example, a requirement could specify the voltage to be used by a system, and another requirement could specify the maximum power that a system could consume. The meaning to a systems engineer is that these are constraint requirements which are constraining the design space. However, to an electrical engineer, these values are properties that they can then use in electrical circuit design and allow the current flowing to the system to be calculated, because power equals voltage multiplied by current. So there's rich meaning there for the electrical engineer. the systems engineering application doesn't know the power equations, but the electrical engineering application would know those equations and would be able to make use of that on behalf of the electrical engineer, for example.
Thank you very much. I have another one from Roy. He's asking if you have an example of a connection to MATLAB, or if you have any information on that.
We don't have a connector yet to MATLAB. We're working on that and developing the requirements for that. And in fact, we're looking for user stories on how users would envisage using MATLAB or Simulink to connect to a GENESYS repository. So certainly if there are users out there who are willing to share their use case and their user stories about how they currently work and would envisage working in the future, we'd gladly be interested to hear that. They wouldn't have to exchange any proprietary data. It's more the process flow that they would be following and the types of information that they're interested in that we'd be interested in learning about.
All right, thanks. So Roy, if you're interested, please reach out to us and we'll get you in touch with our development and engineering team for that. And then I do have one more question. This one is from Leslie, and she asks, what programming language could we use to develop an application that accesses the API? And what else are we likely to need?
Okay, so the API is implemented using Windows.NET technology, as I mentioned. So really any programming language that can use the .NET libraries is appropriate. So something like C# or Visual Basic .NET. It needs to be the .NET version of Visual Basic. Aside from knowing the programming language and having GENESYS, I think the only other item you're likely to need is an editor to create the software with. But if you're able to, using an integrated development environment such as Visual Studio does offer benefits such as IntelliSense, so that the .NET classes, methods, and properties are exposed to you as you use that developer environment. But that's really all you need, I think.
All right, thank you so much. As the audience members, as you guys absorb this information, if you find that you have additional questions, you can go ahead and reach out to us at Vitech. We'll get that information over to him. We do have a contact us link on our homepage at vitechcorp.com. You could also post onto the Vitech LinkedIn group that is monitored. Just visit linkedin.com and search for Vitech Corporation. Apply to be a member of that group, and I'll get you processed and in there. Thank you so much to everyone for attending today's webinar. Please keep an eye on your inbox for our next webinar invitations coming in a few weeks. You can also stay up to date in all of our upcoming webinars by visiting our webinar calendar on the services and training area of our website, again at vitechcorp.com. And just one more note, at the conclusion of this webinar, a survey should open up on your screen. Please take a moment and give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you so much and have a wonderful day.